Yeah, so this is the energy presentation part two, where we'll talk about conservation of energy. But I want to go back to this slide. I took a look at your tests and your quizzes and your content and realized that it's a slightly different than how I typically teach this unit because I don't do springs until later. But this, the Georgia Virtual School content does it now. So the total mechanical energy is all the mechanical energy, which is kinetic energy, potential energy, and spring potential energy. So you get a 1/2 mv squared plus mgh plus 1/2 kx squared. So we'll continue this with the conservation of energy, a recognition that energy can change from any of these types to the others. But spring is another kind of potential energy, just like gravitational potential energy. And in your content, the total mechanical energy is the sum of all three of these: gravitational potential energy and spring potential energy. Okay, let's see, a couple other things that I didn't put in the first presentation. If you have a graph of force times distance, so remember force versus, not force times, but force versus displacement, that puts force on the y-axis, it's y versus x, so displacement on the x-axis. If the area under that is work done. And you will always be able to calculate the area by triangle. It won't be some curvy thing that you'd have to use calculus to find the area under. It will be like a constant force or a constantly decreasing or increasing force, so that you'll be able to find areas of a rectangle, which is base times height, or of a triangle, which is 1/2 base times height. There's another rectangle, and a triangle. It'll be simpler than that. Your graphs will look more like this and then this, so that you have just a triangle as your axis and a rectangle. But it'll be areas that are regular, simple areas that you can find easily. But the area under a force versus displacement graph is equal to the work done. Spring potential energy is 1/2 kx squared, where k is the spring constant. Springs have constants. The units are newtons per meter, and it's how much force it takes to stretch or compress the spring, newtons per meter. And the energy stored in a compressed or stretched spring is equal to 1/2 times the spring constant times the square of the displacement, the square of the amount by which the spring has been stretched or compressed. And that would need to be in meters to match the units of the spring constant. And as I said just a minute ago, the total mechanical energy includes the spring potential energy as well as the gravitational potential energy and kinetic energy. We just talked about the definition of total mechanical energy. Conservation of energy means that through some process, the amount of energy in a system does not change. And so for problem solving, that means that the initial gravitational potential energy plus the initial spring energy plus the initial kinetic energy is equal to the final, let me put initial, is equal to the final potential energy, gravitational potential energy, plus the final spring potential energy, plus the final kinetic energy. So the sum of all three of these before something happens is equal to the sum of all three of these after something happens. Generally, you're not going to have all three. And so your equation could be much simpler than that. An example, a rock falls from a cliff through a distance of 30 meters. So here's our cliff. It's 30 meters high, and a person drops a rock, and it falls that distance of 30 meters. What is the speed of the rock just as it hits? Well, if I look at all my types of energy, what kind of energy do I have at the beginning? Well, I have gravitational potential energy, so there's going to be an mgy or mgh. I do not have any spring energy. There is no spring in this problem. I do not have any kinetic energy at the top, so the total mechanical energy at the beginning is simply mgy. At the bottom, I don't have any potential energy. I don't have any spring energy, but I do have kinetic energy. So the initial potential energy is going to be equal to the final kinetic energy. So that's going to give me an mgy equals 1/2 mv squared. Notice there's m's on both sides, and since there are m's on both sides, they cancel out. And okay, when I work practice problems, I let g equal 10 meters per second squared, because then I can do a lot of the math in my head. I advise you to do that on practice problems, but not on a test or on a lab. You have to use 9.8. So I'm going to let g be 10 meters per second squared, and that height is 30 meters, and that equals 1/2 times v squared. So 10 times 30 is 300. If I get rid of that half, I'm going to have to multiply both sides by 2. So that's going to be 10 times 30 times 2, or 300 times 2 is 600, equals v squared. And let me get my calculator out, which is my phone, so it takes me just a minute to get it open and working. So I need the square root of 600. V equals 24.5 meters per second. Now you could have solved this using kinematics and free fall from the applications, no, from kinematics, from the second unit that you did, and it would have been a much more complicated, difficult problem. Conservation of energy makes these problems really simple. You throw a ball into the air with an initial speed of 30 meters per second. How high will it go? Use conservation of energy, not kinematics. Okay, so here we are with a ball in our hands, and we're going to let this be a 0 height. And the ball is going to go up to here, some height y. Well, at the beginning, think about the 3 types of mechanical energy. We have gravitational energy, potential energy, we have kinetic energy, and we have spring energy. At the bottom, do we have gravitational potential energy? No. Do we have kinetic energy? Yes. Do we have spring energy? No. At the top, do we have gravitational potential energy? Yes, we do. Do we have kinetic energy? No. We've thrown it straight into the air, and how high will it go? When it's as high as it goes, its velocity will be 0, so there won't be any kinetic energy. And there's also no spring energy. And so our equation becomes the initial kinetic energy is equal to the final gravitational potential energy. And so a 1/2 mv squared equals mgy. And if I want y, notice those m's are going to cancel again. Hold on just a second. Okay, there was a little interruption. My phone rang and I had to answer it, but let's get back to this. The initial kinetic energy is equal to the final potential energy, as we determined by considering the beginning and the ending states. Mass cancels out, and so what I'm left with, if I want to solve for y, I would divide both sides by g, and so that's going to give me v squared over 2g equals y. Is that right? If I divide by g over here, and I divide by g over here, the mass is, yeah, okay. So the velocity is 30 meters per second, so that'll be a 30 squared over, and remember I use g equals 10 meters per second squared, and so 2 times 10 is 20. 30 squared is 900 over 20. 90 divided by 2, so y equals 45 meters. So easy peasy. Thermal energy. Where does energy go when it leaves a system? Generally, it's converted into thermal energy. The rock in the previous problem hits the ground and stops moving. So we had this rock that was 30 meters high and it fell to the ground. Well, and then it was sitting there and it wasn't moving. So now it doesn't have potential energy, it doesn't have spring potential energy, it doesn't have kinetic energy, it's just sitting there. Where did the potential energy that it had here, where did it go? Right before it hits, it's kinetic energy. When it hits, it's converted to thermal energy. It makes all of the particles in the ground vibrate, and energy is dissipated, it's spread out. It then moves through the material, but it's converted to thermal energy. If you have a child on a slide, sliding down a slide, or a grown-up sliding down a slide, they have potential energy at the top. They have kinetic energy when they get to the bottom, but the kinetic energy at the bottom will be less than the potential energy at the top because there's friction on this slide, and the whole time the person's sliding down, there's some of that potential energy. Some of it's going to kinetic energy, but some of it is going to thermal energy as well. The slicker the slide is, the less energy is lost to thermal energy, and the more is converted straight to kinetic energy. The thermal energy doesn't mean that energy is not conserved. It is still conserved. It's not destroyed. It's just converted into a different kind. Thermal energy, typically you can't reuse it because it's dissipated and you can't recover that energy. So a roller coaster problem. A cart starts at rest at the top of the first hill of a roller coaster. And the first hill is 50 meters high. How fast is the cart moving at the bottom of the hill? And then we're going to find out how fast is it moving at the top of the second hill if the second hill is 20 meters high. So at the top, do we have gravitational potential energy? Do we have kinetic energy? Do we have spring energy? Well, there's no springs in this problem. So we're going to do top, bottom, and second hill. And there's not going to be any spring energy anywhere. At the bottom, this is a height of 0. And so there will not be any gravitational potential energy. Wait a minute, I didn't do the top. At the top, there is gravitational potential energy. It's stationary, so there's no kinetic. At the bottom, we call that a 0 height, and so there's no gravitational potential energy. It is moving, and so there is kinetic energy. At the second hill, it's not at the bottom anymore, so it does have gravitational potential energy, and it's moving, so it has kinetic energy. So let's consider the first problem, how fast is it going at the bottom? So that equation, the initial potential energy, gravitational potential energy, is equal to the final kinetic energy. So mgy equals 1/2 mv squared. And if we want to know how fast, we're looking for v. So I'm going to cancel those m's. I'm going to multiply by 2. And so v is the square root of 2 gy. 2 from this 2 down here will be up there, and a square root because you have to find v. And so that's the square root of 2 times, remember I used 10 for g, and the height is 50. And 10 times 50 is 500 times 2, that's the square root of 1,000. Let me get a handy dandy calculator. It takes me just a minute to get, there we go. And 1,000 square root is 31.6 meters per second. Okay, so how fast is it moving? The cart goes here, and then the cart goes up to the top of the second hill, and how fast is it moving there? Well, if we look at our energy types, we have both potential and kinetic at the top of the second hill. So the potential energy at the top now has to equal the potential energy at the top of the second hill. I'm just going to call it final, plus the kinetic energy final. It has potential and kinetic energy at this hill. So again, we have mgy equals mgy2 plus 1/2 mv squared. Look, it's got m's everywhere, so they can all cancel out. And I'm looking for that value. So that's going to be a gy minus gy2 equals 1/2 v squared. That's actually g times y minus y2. And I'm going to multiply both sides by 2, so 2g y minus y2 equals v squared. So if I want it to equal v, I have to take the square root of both sides. So the square root of 2 times 10, and y minus y, 50 minus 20 is 30. 10 times 30 is 300, and 300 times 2 is 600. And so what we're looking for is the square root of 600. And I get 24.5 meters per second. Of course, it's going slower at the top of this hill than it was at the very bottom. This is the fastest, at the bottom is the fastest it will go anywhere. Okay. Next. Suppose we're going to talk about some spring stuff now. Suppose a block of mass 2 kilograms is moving with a velocity of 10 meters per second. So 2 kilograms, 10 meters per second, and it's moving this way. It comes in contact with a spring. Let's put a wall there. How far will it compress the spring? So this is before anything happens. Then that spring gets compressed. As the block moved, the spring was out here. When the block hit it, the block compressed the spring a distance x. How far will it compress the spring before stopping? The spring constant is 2 newtons per meter. So let's look at our energy types. We have gravitational potential energy, we have kinetic energy, and we have spring energy. We have before, so let's just say 1, like over here. We don't have any gravitational potential energy anywhere because everything's flat. We do have kinetic energy at the beginning. The spring is not compressed, so there's no spring energy at the beginning. At the end, there's no kinetic energy because it stops, and there is spring energy. So my equation is going to look like 1/2 mv squared equals 1/2 kx squared. So the 1/2s cancel out, but my m's don't. So if I'm looking for x, it's going to be an mv squared over k, right? Divide k by both sides by k equals x squared. So if I take the square root of both sides, I got a mv squared over the square root of mv squared over k. And that v squared under that radical can come out. It doesn't really matter if you bring it out, you could have it be v times the square root of m over k. We'll do it that way. The velocity is 10 meters per second. The square root of mass, 2 kilograms, divided by k. Oh, this works out nicely, which is also 2. And so 2 over 2 is 1, and the square root of 1 is 1. And so that tells me that x equals 1 meter, which is actually quite a long ways. It's a big spring. Okay, suppose a ball is sitting on a spring. So we have a compressed spring with a ball on it. And it has been compressed a distance of 1 meter. So we had, 0.1 meters. So we had the spring, and we put the ball on it and pushed down and compressed the spring. If the spring is released and it throws the ball into the air, how high will the ball rise above the initial position? That would be above right here. Okay, so before we release it, what kind of energy do we have? Remember, there's gravitational potential energy, there's kinetic energy, and there's spring potential energy. At the beginning, so here, there is no, we're going to call this the 0 meters because the ball is going to go here and we're looking for the height above that initial position, not really above the ground. So that's going to be our y. So there's no gravitational potential energy, there's no kinetic energy, there is spring energy in that compressed spring. And then at the end, when the ball is way up here, it has stopped, so there won't be any kinetic energy. It's not on the spring anymore, there'll be potential energy. So our equation is going to be that initial spring energy is going to equal the final gravitational potential energy. So we have a 1/2 kx squared equals mgy. And 1/2 times the spring constant is 5. It was compressed a distance of 0.1 meters, and we have to square that, equals the mass. I didn't give you the mass. Let's let it be 2 kilograms. Sorry. Times g, which I let g be 10, times y. 0.1 squared. Let me get my calculator going again. 0.1 squared is 0.01 times 5 divided by 2 is, on this side I get a 0.025 equals 20y, 2 times 10. So divide 0.025 by 20 divided by 20. And I get a y equals 0.00125 meters, which is a very small distance. But it's a pretty weak spring, and it's 2 kilograms is about 5 pounds. So, all right, so it doesn't go very high. Elastic and inelastic collisions. We talked about this, or I guess we will talk about this in momentum. The difference is kinetic energy is conserved in an elastic collision, but not in an inelastic collision. And that is the end of this presentation, and I hope you found it helpful.